Hello everyone. In last lecture I was discussing about fatigue life estimation by fracture mechanics approach. There I have already completed Paris law. Using Paris law, how to estimate the fatigue life of a welded structure, that related details I have already discussed. Today I will discuss about another weld life estimation method, that is nominal stress method. So, this is the content of today's lecture. Today I will discuss about what are the other different types of fatigue life estimation methods are there, for especially which are used for welded structure. Then I will discuss about fatigue life assessment by using nominal stress approach, and finally I will discuss about some problems or some examples related to nominal stress approach. So, the method of structural fatigue we know that can be grouped into, you can say, following three categories. This I have already briefly discussed in some earlier lecture. So that what are those groups that I am just showing. First of all, the method of structural fatigue, one category is fatigue analysis method, another category is fatigue design method. This fatigue analysis method and fatigue design method I have already discussed, and the last method, last category is called fatigue life estimation method, by which we can estimate the fatigue life of a structure. So, this fatigue life estimation method, you can say generally the method which are used for estimating the service life of different types of structure, which are based on stress strain, or you can say stress intensity factor, because in this lecture I will discuss about other different types of fatigue life estimation method, and also I will discuss today one of the very important fatigue life estimation method which are popularly used in welded structure, that related things also I will discuss. So, these fatigue life estimation method are based on especially in strain stress or stress intensity factor. So, in practical engineering application, there are many kinds of fatigue life prediction methods are available that we are well familiar. Among these, the most commonly used method you can say are stress life analysis method, strain life analysis method, fracture mechanics method. These three methods which I have already discussed in previous lecture, and the last method which is called stress field intensity method. So, this stress field intensity method related things I will discuss in subsequent lecture as well as in today's lecture. So, the fatigue life you can say estimation method of steel structure such as bridge, offshore structure and ships, etc., may be mainly categorized into two groups. So, whatever the method generally we use for welded fatigue life estimation, or you can say in general the fatigue life estimation of different other structure which have a wide application in manufacturing field, this estimation method can be categorized into two groups. One is called global method, another one is called local method. The global method is the most you can say common method, and which is the simplest method that you can say. So, the simplest and most common method also categorized as a global method, which is the you can say nominal stress method, which I will discuss in today's lecture in details. The other method which is categorized as local method, in this local method the following different types of categories of fatigue life estimate method are come into this group. Like what happens, one is called the hot spot stress method, the effective NOS method, and another one is called crack propagation approach using LEFM. LEFM already I have discussed in detail, that is linear elastic fracture mechanics approach. This already I have discussed this fourth method. So, the rest three method, the first method is nominal stress method which is called global method, and another two method that is hot spot method and effective NOS method which are called you can say local method. That related things in details I will discuss in subsequent lecture. So, a common characteristic factor for this first three, that means nominal stress method, hot spot method and effective NOS method. In this first three method, a common characteristic factor is that this method generally considering linear elastic theory, always you should keep it in mind. This first three method generally is, that means this method and this method. This first three method is based on, you can say, a common characteristic factor, and this method considering the linear elastic theory. And in this method generally we use numerical method such as finite element method, FEM, in short it is called FEM. Then also we use BEM, means boundary element method, and this method are based on what it is called SN curve classification, always you should keep it in mind. So, in this method we use SN curve to estimate the life. So, this first three method, one is global method, another two is local method. So, this method generally considering the linear elastic theory, and in this method generally we use numerical method such as finite element method or boundary element method to estimate the stress field distribution, that we can say, and also this method also based on SN curve classification. By this generally we estimate the total life of that structure. This you should keep it in mind. Whereas the another local method, that is crack propagation approach, or you can say linear elastic fracture mechanic approach, that is the fourth method, which are based on principle of fracture mechanics. This you should keep it in mind, which I have already discussed, which generally covers crack growth, and this method is independent from any SN curve. This you should keep it in mind. So, in fracture mechanics approach, SN curve data is not required. Now, some more details also we should know about this different types of fatigue life estimation method. Generally, for fatigue life estimation method, the stress parameter used in fatigue assessment method are presented here. You can see, like let us consider this is a welded joint, a T welded joint, you can say. Here this is fillet weld, you can see. So, if it is subjected to a axial force F, then how the stress distribution over the you can say weld toe region to, you can say, away from the weld toe region, that I have shown here. So, you can see near the weld toe region the stress distribution is looks like this along the cross section. If we just go little bit away from weld toe region, what is weld toe? Weld toe, you know, let us consider, I have already discussed these things in details. Then also I should tell little bit here. So, you see this fillet welds, this is called weld toe. Okay, this is one weld toe, this is another weld toe. These are the critical zone, you can say, of a welded joint, and this is generally called joint root. This is called joint root. This you should keep it in mind. So, if we do the welding, generally at this welding some penetration is taken place. So, for this let us consider this is the weld joint. So, in this case at tip of this penetration depth, that is called weld root. Joint root is the corner point of this T joint, and whereas you can say weld root is the after welding some penetration is taken place. So, along this joint root line, whatever the depth of point we get, that is generally called weld root, that we can say. So, you see, so this weld root and weld toe are the critical point of a welded joint. So, from this weld root and weld toe, how the stress distribution is taken place, that I have shown. So, you see, if we go away from the weld toe region far away, then we can observe that the stress distribution throughout the thickness is uniform in nature. Okay. So, where the stress distribution is uniform in nature, this zone we can consider as the nominal stress region. Now, we know what is nominal stress. Nominal stress in detail also in subsequent slide I will discuss. Nominal stress generally we define as force divided by minimum effective cross sectional area. This you should keep it in mind. This I have already discussed in earlier lecture little bit details. So, here also I will discuss these things in subsequent slide in details. So, you see where the stress distribution is uniform throughout the thickness, this zone you can consider as nominal stress zone. So, here you see the stress is not varying along the direction of this well toe, that you can say. So, here stress is not varying. If we go little bit closer to the what it is called well toe region, due to this structural distribution or structural discontinuity, this stress distribution pattern changes, or you can say there is occurs some stress concentration. That is why you can see the stress variation is start, and what happens at well toe you can observe that there is coming maximum stress due to stress concentration at well toe region. What I am telling, understand? So, that related things here we have shown. So, what happens? So, nominal stress zone is that zone where generally stress distribution throughout the thickness is uniform, whereas hot spot region is that zone where the stress distribution throughout the thickness is start varying, that you can say. That zone is called what is called hot spot zone. So, hot spot stress generally we calculate using some very standard method are there, like what happens here, this is one point and this is another point we have taken. These 2 points are little bit away from the welt root point, let this is one point and this is another point. So, this 2 point stress we first connect, after that we extrapolate these things till point let us P. This P point is at the location of well toe. So, along the location of the well toe, whatever the P point, after extending this 1 2 line, whatever the point it is cutting, that and this point whatever the stress we got, that stress is called generally hot spot stress. Like one of the example, like I am telling, this point 1 generally have a distance from this well toe little bit where the non-linear stress is started. So, this point you can say is around 1 T, 1 T is the thickness of the plate, this T is the thickness of the plate which I have already given, and the point 2 have a distance from the well toe which is generally in some cases it is considered as 0.4 T, one of the method I am just telling. So, at 1 T location whatever the stress is there, so at that stress at top surface whatever the stress is there, that stress point, and what happens another point we need to take, that is the distance at a distance of 0.4 T from the well toe, at that location whatever the stress is there, this 2 stress, by this 2 stress if we draw a line 1 2, this line 1 2 once we extrapolate or extend along the direction of well toe region till well toe location, wherever it is cutting, at that location whatever the stress value we will get, that stress is generally called hot spot stress. This you can say. We can estimate what it is called by using some numerical method, like I have already, one of the popular method is called finite element method. What I am telling, understand? And if we just calculate the stress value at well toe location by this finite element method, let us we got another stress magnitude that is at well toe, that is the point P1. So, at the P1 the stress rises due to what? Stress concentration due to toe effect, well toe effect, that you can say, because the well toe is such a point where sudden abrupt change, or you can say sudden change of the geometry is taken place. That is why here some geometrical changes effect is coming in stresses. That is why what happens here, due to these geometrical changes here, stress concentration is taken place and stress rise drastically. So, at P1 point whatever the stress we got, that stress generally we use in Gauss stress method, that you can say, which is non-linear stress peak, that you can say. What I am telling, understand. So, these are the different stress value we use for different method. This you should keep it in mind. This stress distribution pattern depends, in case of fatigue analysis, is how the load is applying on that structure. That is why I have written fatigue loading is the most important parameter which influencing the fatigue strength of the structure. This you should keep it in mind. Fatigue strength of the structure means this fatigue loading is responsible for developing these stresses. That is why what happens, if the fatigue loading will be different, then different stress distribution will be there, and what it is called, different fatigue life also will be there for that structure. That is why I have already written fatigue loading is the most important parameter which is influencing the fatigue strength of the structure. So, in case of fatigue analysis, I have already discussed this thing. There are mainly two important parameters for defining the fatigue load fully, which is called stress range and another is called stress ratio R. So, based on this stress range and stress ratio, you can say in case of fatigue loading cases, a fatigue loading is divided into two different types. Okay. These two different types fatigue loading is divided with, is based on, you can say, loading history. So, one of the load is called constant amplitude fatigue loading, another types of loading is called variable amplitude loading. So, this constant amplitude fatigue loading is called CAFL in short form, you can say, and variable amplitude fatigue loading in short form you can say as VAFL. This you should keep it in. But here I have already shown constant amplitude, what it is called fatigue loading means with respect to time, if the amplitude is not changing. What is amplitude? I have already discussed. Amplitude means sigma max minus sigma min divided by 2. So, this sigma A in a if sigma A is not varying over time, that is generally called CAFL or constant amplitude fatigue loading. If this sigma A is varying with time, that is called variable amplitude fatigue loading. So, you see generally these types of you can say different types of, in figure 2 you can see different types of constant amplitude fatigue loading I have shown. Here this fatigue loading is grouped based on, you can say, this stress ratio. What is stress ratio? This stress ratio R you can define as sigma min divided by sigma max. I have already discussed this thing. So, you see, so this you can say CAFL have different categories, like some CFL which have a R value greater than 0, some CFL which R value is equal to 0, this category. Okay, this is generally called repeated types of loading, you can say. For reverse types of loading, you can see here you can say R value is less than 0 and you can see where R value greater than 0. These are the different categories are there. Okay. Whereas variable amplitude fatigue loading also, you know, here the load history is varying with time. That means here the load amplitude is varying with time. So, you see, depending upon this load history, generally fatigue strength is varying. This you should keep it in mind. That means fatigue strength is dependent on these types of load history. That is why I am just showing these things. Now, this fatigue life assessment method mainly grouped into 4 methods. So, these 4 methods which are we used to predict the fatigue life of a welded component, this group was, you can say, decided by a society. That society in you can say is called IIW. Okay. This IIW fatigue design recommendation which recommend that these 4 different method which can be popularly used in the field of what it is called welded component fatigue life estimation purpose. You can't use for each purpose. What I am telling, understand, for a particular method you can use for a particular types of welded joint. So, that related things in details I will discuss in subsequent lecture as well as in subsequent slides. So, this IIW, you know, the full form of IIW is International Institute of Welding. So, it is called International Institute of Welding. Okay. IIW fatigue design recommendation group the fatigue life estimation method for welded components are as below, like nominal stress approach, which I will discuss in today's lecture. Another one is called structural or geometrical, or it is also called hot spot stress approach. Then third approach is called effective notch approach, which I have already told you, and linear elastic fracture mechanics approach, which I have already discussed in earlier lecture. And finally, IIW also recommends that if this 4 method is failed to determine the fatigue life of a welded structure, there we can use this lab testing also. This lab testing you can use for all types of welded joint, but this lab testing generally is a very costly and time consuming phenomena. That is why what happens, other 4 method you can use for some particular types of recommended structure are there. So, for those types of structure, this 4 different method we can successfully use. Where this 4 different method is fail to use or fail to determine the fatigue life, there also we can use this lab testing method. Lab testing method we can use for any types of welded structure. What I am telling, understand, this you should keep it in mind. That is why here I have shown. So, here the nominal stress method and hot spot method generally suitable to simpler weld geometry, that what I have already told you. So, all the method you can use for all the purpose. Generally the simpler types of weld geometry, there we can use these 2 method. One is called nominal stress and hot spot method, and this nominal stress and hot spot method generally used to determine the fatigue life of weld toes. This you should keep it in mind. They generally in a weld joint there are 2 critical points are there, which I have already told you. One is called weld toes, another is called weld root. So, these 2 points generally this nominal stress and hot spot method mainly used for weld toe. But what happens, you can apply this method in weld root purpose also. What I am telling, understand, this you should keep, that also I will show, but it is mainly used or it is recommended to use only in weld toe. The nominal stress method is generally based on pre-existing fatigue class, this you should keep it in mind. Whatever the nominal stress method we will use, there will be required a fatigue class. Fatigue class means a set of welded geometries SN curve data is available, which is generally pre-existing. That data is determined experimentally. This you should keep it. That data is required for nominal stress method. This you should keep it in mind. And that data set generally is estimated for a particular set of different weld joint. That is why I have already written, and this method is limited to evaluation the weld toe, not the weld root. Some references, some researchers are told it is not recommended to use weld root, but what happens, you can use this thing in weld root also, that also I will show. That means if we can predict the nominal stress in weld root, there also we can use, but it is recommended to use these things in weld toe region, this nominal stress method, this you should keep it in mind. The hot spot method generally is based on geometrical stress from the structure, which I have already told you. Generally nominal stress method where the stress is through the thickness already almost uniform, you can say, whereas where the throughout the thickness the stress is start varying, from that region generally we extrapolate the stress and we calculate the stress at well toe by this extrapolation method. By using this stress value, generally we calculate the what it is called fatigue life of that welded joint. Okay. That is why here I have written hot spot method is used for evaluation. Here also this is also evaluation for simple geometry and only the well toe. What I am telling, and this is also mainly used for well toe, that you can say. Now the another method, that is called effective NOS method. This effective NOS method is a method which I have already told, where the generally you can say the stress which we are considering in well toe region, that stresses generally I have already told is rising due to this toe effect, as well as in root, whatever the stress will get at root effect, because there is generally occurs some abrupt changes, that due to this thing there is occurs some, you can say, well toe act as a NOS, that you can say, due to this thing there generally the stress rise drastically. So using those stress, generally what happens, you can predict the fatigue life, that method you can consider as effective NOS method. But for estimating that method, generally here we use a effective NOS instead of actual well NOS. Here we used a effective NOS. How it is, that I will discuss here. So effective NOS method can be used to evaluate both well toe region life as well as well root region life. This you should keep it in mind. And this effective NOS method also can be used for more complex structure. Generally I have told you, nominal stress and hot spot method generally used for, mainly used for well toe region, and it is also those two methods also used for generally simpler types of geometry, whereas effective NOS method can be used both well toe and well root region, as well as if the structure is complex in shape and geometry, there also we can use this effective NOS method. So here, according to International Institute of Welding, here generally an effective radius of 1 millimeter is model in the well toe. This I will discuss in details, how this 1 millimeter effective radius is model in well toe as well as in well root, that I will discuss. So generally according to IIWA, effective radius of 1 millimeter generally is model in the well toe as well as well root under condition. What is the condition? The condition should be where no post heat treatment has been applied. That means in that well there should not be any post weld heat treatment. Okay. As well as the another condition is the weld or you can say welding quality is normal quality, and base material should have a thickness which is greater than equal to 5 millimeter. So for that, if that means if our thickness of the plate greater than 5 millimeter, then welding is normal, no post weld heat treatment is applied there. There generally this you can say effective NOS method we use. Generally we need to create a effective NOS of radius 1 mm. This you should keep it in mind at well toe and well root region. After that, generally what happens, we need to find the stresses value, that I will just discuss in a subsequent point. Like, so after creating this effective radius 1 mm at well toe and well root region, this method generally define the NOS stress at the well toe and well root when the real radius is replaced with an effective radius. What I have told you, generally whatever the root radius and what it is called toe radius is there, that is generally replaced with a 1 millimeter radius. When the 1 millimeter radius we will use once the plate thickness is greater than equal to 5 mm. This you should keep it in mind. Okay. So for that after creating that notch radius of what it is called 1 millimeter at well toe and well root, after that once we calculate the stress, that stress generally we use in effective what it is called notch method to estimate the fatigue life of that structure. Hence, the effective notch stress is not a real stress, but an idealization. This you should keep it in mind. So, this is a idealization method, this you can say, but this method provide you a very accurate result, this you should keep it in mind. So, we got different idea about different life estimation method. Now, we also should know fracture mechanics method. This fracture mechanic method also can be used both in what is called well toe as well as in well root region, that I have already discussed. So, fracture mechanics can be used for a complex structure like effective notch method, and it is based on crack propagation, and this method can be used to evaluate fatigue life of well toe as well as well root. But fracture mechanics have a drawback. Why? What is this drawback? Because we have already seen that for fracture mechanics generally we need some extra material information, material data information. That is why I have written fracture mechanics has a drawback compared to effective notch method, since it require more information about the material properties. Now, the effective notch method and fracture mechanics method are more suitable to generally more complex geometry. This also you should keep it in mind. Now, the last point which you need to note. So, these are all whatever the method I discussed, these are all you can say some approximation, or you can say some assumption we use there, okay. But the more accurate result we can get if we use lab test. This lab test can be used to determine the fatigue life of weld ends, but this method is time consuming and costly method. That is why the other method is very popularly used, which is generally less time consuming as well as less costly. Now, I will discuss here in details about a nominal stress approach first. So, here in nominal stress method I will discuss in details what are the steps generally we use to estimate the fatigue life, and what are the different generally data required for estimating the fatigue life using nominal stress, that related things in details now I will discuss. So, first method which I am going to discuss is nominal stress approach. So, the nominal stress approach is the simplest and I have already told you most common applied method for estimating fatigue life of steel structure. Mainly it is widely used in steel structure. So, this method is mainly based on which I have already told you average stress in the studied cross section considering the overall linear elastic behavior. So, here we consider linear elastic behavior. Here the local stress rising effect, whatever the local stress rising effect like at well toe or you can say well root, that local stress rising effect of weld and the attached plates generally here we ignored. So, local stress rising effect of welds and the attached plate are ignored in the nominal stress calculation. This you should keep it in mind, because it is assumed that the connection specific SN curve which will be used for this nominal stress approach, there generally we consider what is called this effect. That is why here I have written, it is assumed that the connection specific SN curve already characterizes these influences. That is why what happens in nominal stress approach, what is called local stress rising effect generally is not considered, or whatever the extra part or the attached plate are there, like what happens, let this is a geometry, here a separate plate we attached, let this is plate 1, this is plate 2. So, let us in case of fatigue life estimation of plate 2, this extra attached plate effect is not considering here. Why it is not considering? Because it is assumed that whatever the SN curve data available which will be used for in nominal stress method, that SN curve data already consider those effect. That is why in nominal stress calculation, once we calculate the nominal stress there, this things or stress rising effect we ignore, because this stress rising effect already it is assumed that consider in SN curve data, or you can say fatigue class data, because that also I will show you what is fatigue class data. In that fatigue class data, generally this effect already considered there, based on those effects generally it's calculate the SN curve. That SN curve effect or that SN curve data we will use in nominal stress approach. The stress rising effect of the geometrical configuration or irregularities of the main component like large cut out must be included. But here one thing you should keep it in mind, the stress rising effect of the geometrical configuration or irregularities of the main component should be considered in nominal stress approach. Like one of the example I am just showing. In case of nominal stress method, let us what happens, we are going to analyze a welded structure where welding is done here. This is the weld zone. So, here you see for these types of structure, this is a fillet types of a structure to what it is called dissimilar thickness plate. So, for this case let us consider it is subjected to a load F. So, for calculating the nominal stress, here we should consider the effect of this discontinuities. That is why what happens once we go for calculating the nominal stress for this case. So, here the nominal stress should be will be F by the this is the diameter of bigger diameter is capital D, smaller diameter is small d. So, sigma nominal should be F by pi d square by 4, not pi capital D square by 4. This you should keep it in mind. Okay. So, a smaller dimension we need to consider, a smaller diameters we need to consider. That is why here we have written.